Okay, so today we are starting something new old. It's new to this year, but it's old to you guys. Y'all have done this before. Where's everybody? Good grief, this whole row. Jonathan? Where's all your people at? So we're going to talk today about Pythagorean theorem and also some trig functions. We're going to go to some special right triangles that you guys have probably studied in the past, but not put them together with your trig functions, maybe. I don't know. We'll see. You maybe haven't done the last thing we'll do today before. But anyways, we're going to go through some stuff that should be relatively familiar in some cases, but then also some things that maybe not as familiar. So let's go ahead and begin. So the first thing we're going to talk about, I know you guys are comfortable with, and that is Pythagorean theorem. Pythagorean theorem is only for what kind of figure? What kind of triangle? Not just triangles, but right triangles. What does it mean to be a right triangle? It has to have one of the three angles being 90 degrees. So if one of them is 90 degrees, the other two are less than 90 degrees, right? And what do we call less than 90 degree angles? A cube. So a right triangle always has one angle that's 90 exactly, and then two angles that are less than 90, right? Because they have to add to equal 90, right? Because all triangles angles add to equal what? 180. So if 90 is gone, you only have 90 remaining. So that's the rule. It has to be this way, okay? So when we're dealing with these right triangles, when we have one angle that is a right angle, we have three sides. Two we call our legs, and then the one that I call the main one is called the hypotenuse. What do you know about the hypotenuse? What do you know? What are some things you know about the hypotenuse? Okay, it's always opposite, and I'm going to say it differently than what you said. It's always opposite the 90 degree angle. It's always opposite the 90 degree angle. What else do you know about the hypotenuse? It's always the biggest side. It's always the biggest side, right? Y'all know that? Did y'all know that? It's always across from the 90 degree angle. It's always the biggest side. Okay? Now, because of the relationship in this right triangle to these sides, you can always find a missing side if you've been given two. Because they always follow the same formula. It's called the Pythagorean theorem. And that Pythagorean theorem is a squared plus b squared equals c squared. A squared plus b squared equals c squared. Again, here are the keys to that equation. C has to be your hypotenuse. You have to put your hypotenuse on the side that is alone, right? No brainer, but sometimes people don't do that. So C has to be your hypotenuse, and it has to be the one that's on the side alone. Okay? So when we come across a problem like number 1, what's the first thing I would want you to think? What was the first thing that I would want you to recognize? Exactly. I would want you to immediately go to your 90 degree angle and say, hey, which one's my hypotenuse? In this case, it's x, right? It's our missing side. Our missing side is the one that we want to find in this particular problem. So I'm going to put the other two that we call legs in A and B's position. Does it matter which one I call A and which one I call B? No, absolutely does not matter. So I'm going to just go A squared plus b squared equals c squared. And then I'm just going to get my calculator out and go 4 squared plus 8 squared is. Anybody got it? 80. So 4 squared plus 8 squared is 80. So is that my answer? No. That's c squared, right? We don't want c squared. We just want c, right? So how do we just get c? We take the square root of 80. All right, let's go over here to the left side real quick. And let me remind you guys of some things. Is 80, can it break out of that radical by itself completely? No, because it's not what we call a perfect square. Y'all remember perfect squares? Perfect squares are the only things that are allowed to break out of a radical, right? So remind me, what are perfect squares? Don't tell me what one is. Like, don't give me an example of a perfect square. What is a perfect square? It's a number that you get when you do what?
When you multiply it twice.
When you multiply something by itself, right? So 1 times 1 is? 1's a perfect square. 2 times 2? 4 is a perfect square. 3 times 3? 9. 4 times 4? 16. 5 times 5? 25. 6 times 6? 36. 7 times 7? 49. 8 times 8? 64. 9 times 9? And then 10 times 10? 100. We'll stop right there. Okay? I don't think you'll need anything bigger than this. And if you do, we'll get to that when we have to. Alright, so look. 80 is not on that list, is it? That's why you can't type in your calculator square root of 80 and write the answer down. We want to simplify this. So we start thinking, well, what's the biggest perfect square that I can take out of 80? So I like to divide by 2. 80 divided by 2, that's the smallest thing you can divide something by, and that gives me 40. Don't try a perfect square above that 40 right there. So 36 is the first one I'm even going to try. Well, 36 go evenly into 80. Just type it in real quick. 80 divided by 36. Does that go evenly? Okay, try the next one. 25. 25 go evenly into 80? Okay, so try the next one. 16. Does 16 go evenly into 80?
Yeah.
How many times? 5. So 16 goes into 80 5 times. Well, why would I do that? Because 16 is a perfect square. What does it get to do? It gets to escape. It gets to come out of your radical as a what? As a 4. So 4 times the square root of 5, that is my hypotenuse. 4 square root of 5. Now remember earlier I told you guys the hypotenuse was the biggest side? Well, does 4 square root of 5 look bigger than 8? Just in the number? It might not. Just type in your calculator real quick. Type in square root of 80. Push enter. Type in 4 times the square root of 5 and push enter. What'd you get? Did you get the same thing twice? Okay, here's the point. I know that we talk about simplifying radicals, and my expectation is that you can do them. But if you can't simplify a radical on an EOC or an ACT test, can you still come up with the right answer? If I'd gotten this problem all the way down to the square root of 80, but square root of 80 wasn't in my choices, could I have picked the right answer? I hope so, because what did you get when you typed in square root of 80? You got 8.94, didn't you? What did you get when you typed in 4 square root of 5? Same thing, 8.94. So even if you can't simplify radicals, which I hope you can still get these problems right because they have the same value, right? Same value. All right, so let's finish this problem up. Actually, it's done. We are done with this problem. Moving on. Number 2, again, what's the first thing I want you guys to notice? Where is my hypotenuse? Well, there's my 90-degree angle. It's across from it. So my hypotenuse is 24. So my 2 legs are x and 22. So here I go. X squared plus 22 squared equals 24 squared. What do I need to do to solve this problem? Subtract 22 squared.
Well, solve the 22 squared and then subtract it.
So you like to go ahead and type in 22 squared in your calculator? Okay, what'd you get? What is 22 squared?
484.
Huh?
484.
And what is 24 squared?
576.
Okay, so what will I do to get x squared alone now?
Subtract 44.
From 576? What is 576 minus 484? Okay, so x squared equals 92. Now what? We're going to take the square root of it. So x will equal, well, let's see about this, 92. 92. Is it a perfect square? No. Divided by 2 is 46. Don't try perfect square above 46. First one below 46 is 36. Does 36 go evenly into 92? Nope. Next one, 25, I know does not. How about 16? I don't know about 16. Does 92 divide evenly by 16? No. 9. Does 9 go evenly into it? No, it goes into 90, not 92. How about 4? 4 goes in there how many times? 4 goes in there 23 times. So which one gets to escape the radical? The perfect square, 4. 4 comes out as a, so my answer is 2 square root of 23. Now I know that's not beautiful, all right? It's way better when it can work out as just a nice number, but that's reality, okay? All your answers in math are not always going to be just perfectly beautiful, all right? Most of you guys probably would say they never are. But anyways, this one was a radical, and that's okay. 2 square root of 23 is your solution for that leg. Questions about that? Y'all feel okay about it so far? Okay, then let's move down to what might be a little bit newer topic to you guys. And I know that y'all did cover this, but maybe since you slept several days since then, or maybe even last year, maybe you didn't quite get to it. I don't know. You got to it before all the COVID stuff hit. But anyways, trig is not as hard as we kind of sometimes make it. It's a very simple idea that just basically says this. The way that your side lengths in a right triangle relate to each other will always follow a certain pattern. And those terms that will always compare the different sides, the various sides of a right triangle, are called sine, cosine, and tangent. Okay? Sine, cosine, and tangent. So the way these always relate to each other is this. So, ka, toa. So, ka, toa. So is S-O-H. Ka is A-C-A-H, and then toa, T-O-A. That's the way these will always follow, they will always follow the relationship that these sides make to each other, and therefore these trig functions will always give us the value in right triangles. Okay, we can use them in a couple of different ways. So first of all, what you need to realize is, like I said, it's in a right triangle. Okay, and because we're dealing with a right triangle, remember there are two angles that are acute, right? But we're only going to name one of them this thing we call theta. Okay? Theta. And that's going to be significant because it's talking about the specific angle, the specific acute angle that we're basing our sine, cosine, and tangent off of. Okay? So here is the trig functions and how they work. Sine is S-O-H. Well, look at this, guys. According to theta, there are two legs, right? The hypotenuse is the hypotenuse. There's nothing you can do about that. But there are two legs. The leg that touches it is called the adjacent leg. The leg that does not touch it is called the opposite leg. Okay? Now I need you guys to understand something. What if I wrote theta up here? Would this still be the opposite leg? No. This would then be the adjacent leg. If we're coming from this angle, so it's all based on which angle you're coming from. From this angle right here, the hypotenuse is the hypotenuse. The opposite leg is the leg that doesn't touch it. The adjacent leg is the leg that does touch it. But don't forget, the hypotenuse is the hypotenuse. But here's how sine works. Sine of that theta angle is the opposite leg over the hypotenuse. S-O-H. Opposite leg over hypotenuse. Can y'all remember that? So what do you think ca means? C-A-H. Cosine of that angle is what? A-H.
Adjacent.
The adjacent leg over the hypotenuse. And then finally you have tangent. That's TOA. TOA. So tangent is opposite leg over adjacent leg.
So is that the same thing as the first?
Nuh-uh. Remember, the first one was opposite over hypotenuse. But tangent is opposite over adjacent. Okay? So it's just your legs. Now, you also have these things we call them the reciprocal functions. The reciprocal functions are, I guess, a little harder to remember. You kind of want them to look the same, like tangent and cotangent. Those are easy. But sine, the reciprocal function for sine is cosecant. So listen, if sine is opposite over hypotenuse and cosecant is the reciprocal function, what do you think that means we do? We flip it. So cosecant is hypotenuse over opposite leg. We flip our sine. Secant is the reciprocal for cosine. So if cosine is adjacent over hypotenuse, secant is hypotenuse over adjacent. And then the one that makes the most sense is cotangent. So if cotangent, or if tangent is opposite over adjacent, what's cotangent? Adjacent over opposite. Okay, so what does all this mean? Like what's on purpose? Well, if I wanted to find the measure of the actual angle, or if I wanted to use the measure of the acute angle to find the length of a side, the relationship between this right triangle always follows the same format. Therefore, sine, cosine, and tangent would allow me to find the missing side length or a missing angle. You understand? That's the purpose. Okay? So, number 3. Find theta. Y'all see it? According to theta, what is the opposite leg? 16. Label it. According to theta, what's the adjacent leg? 30. So what does that make the side that I don't have? The hypotenuse. How do we know that is truly the hypotenuse? It's across from the right angle. And what do we not know about it? We don't know how long it is, right? So let's combine what we just learned with what we just learned. How do I find that hypotenuse? We got to go back to what? Pythagorean theorem. We don't have what? We don't have C. We have A and B, and it doesn't matter which one they are. So 16 squared plus 30 squared equals C squared. So grab your calculator, go 16 squared plus 30 squared. Anybody? Did you get 1156? 1,156.
I got 250. Oh, wait.
I got 11.
1156 equals c squared. So what do we need to do to find c? Take the square root. Now listen, guys. Is that 1156 one of those perfect squares that we wrote over there on the side? No, we only went to 100, didn't we? So if I don't know if it's a perfect square or not, type it in. Square root of 1156 and just see if it is. It is? What does it equal? So my hypotenuse equals 34. So now we're ready to find all these without any real issue. Okay? So, ka, toa. Start with so. What's sine? What's sine? What's the opposite? Over. What's the hypotenuse? 16 over 34 it is. Now, will that reduce?
Yep.
If it will reduce, I like to reduce them. What is 16 over 34 reduced to? 8 over 17. So guys, if sine is 8 over 17, what else do we know easily? If sine is 8 over 17, what else do we know easily? The cosecant. Why? How do we know it easily? It flips it. So it'll simply be, okay, that was easy. Okay, let's find the cosine. Ca, adjacent over hypotenuse. What's my adjacent? Over my hypotenuse? Will 30 over 34 reduce? Absolutely it will. Type it in. So my cosine is 15 over 17 for this particular one. So what's my secant?
17.
That's pretty easy, right? And then finally we have tangent, toa. Opposite over adjacent. What's the opposite? What's the adjacent?
30.
What is 16 over 30 reduced to? So if tangent is 8 over 15, what's cotangent? Alright, and there you have it. Questions about that? Y'all find this to be pretty easy? Because I only have a couple people talking. Sometimes I worry if there's only a couple people talking that there's some who don't understand it. Okay, look at the next one. Here's theta, guys. What's the no-brainer? The hypotenuse is 7, right? Now, according to theta, which leg do they give me? They give me my adjacent leg, don't they? We need to find our what? We need to find our opposite. So here we go. Let's do it. This one's a little harder because we have a leg that is square root of 13. So let me type it or write it in, and then we'll talk about it. Our equation is a squared plus square root of 13 squared equals 7 squared, right? I just plugged them all in. Where they go, a and b doesn't matter, right? So what happens to square root and square? So doesn't that really say a squared plus 13? And what's 7 squared equal? Okay, so we have a squared plus 13 equals 49. Now what? What is 49 minus 13? And when we take the square root of 36, what are we going to get? What's the square root of 36?
6.
So my opposite leg is 6. So y'all ready to answer some questions? Yes.
So is the 13 just 13 with a square root thing on it?
Yeah, square root of 13.
So it's not 13?
No, it's square root of 13. Okay? Remember, square root of 13 has a value. Okay, it's approximately 3 point something. So that's essentially what you have here. You just have a square root of 13. Okay? So here, let's answer some questions. We've already labeled all our sides, right? So what's sine?
6 over
6 over 7, right? So therefore, what's cosecant?
7 over 6.
7 over 6. Okay, pause for a second. See, this square root of 13 is about to give me some issues. All right? So I want to remind you guys of the rule. Whenever we have a radical in the denominator, remember, we don't leave it there. So we rationalize the denominator. That's what it's called. And it's really simple. We multiply by 1. But 1 in this case is the square root of 7 over square root of 7. Does everybody understand how that is 1? You can multiply by 1 all day long, and it may change the way a problem looks, but it won't change the value. For example, 1/2. If I multiply 1/2 by 3 over 3, is 3 over 3 equal 1? 1/2 times 3 over 3 is 3/6. Guys, is 1/2 and 3 over 6 the same value? Yeah, it just looks different. Same thing here. We multiply by 1. Why? Because what happens up top is we're left with 5 squared root of 7. But here's the key. What happens in the bottom? Well, we have the square root of 7 squared. What's going to happen to the square root in 7? Or the square? It cancels, and we'll be left with just 7. We got rid of the square root in the denominator. That's what we mean when we say rationalize the denominator. So here's the point. Look at this next problem. What's the cosine? It's the square root of 13 over 7. That's fine. But what happens when I do the secant? I flip it. And it's 7 over the square root of 13, and we don't leave that there, do we? So we multiply by the square root of 13 over the square root of 13, and that gives me what final solution?
7 with the square root over square root of 13.
No, not square root of 13, just 13. And that is the final answer for that secant. A lot of people let that make it harder, but it's not, okay? We just had to get rid of that radical in the denominator that existed because square root of 13 was left there. Does that make sense? Okay, last one. What's the tangent? 6 over the square root of 13. So doesn't that make the cotangent square root of 13 over 6? Which is fine, right? But the tangent's not. We're going to multiply by what? And that's going to cause the top to be 6 squared root of 13, and the bottom, just 13. And there you have it. And that's all there is to that problem. Questions about it? Y'all feel okay about it? Let's go to the back then. The back adds a little trick to it. It says, given the ratio for cosine, find the remaining ratios. So here's what I encourage you guys to do. Draw a triangle, a right triangle. Label your 90-degree angle, but also label theta. Y'all with me so far? So tell me if I'm right. This value up here is called the what? Hypotenuse. This side right here is called the what? Opposite leg, because of where I put that theta. And then that makes this side the what? The adjacent leg. Y'all with me? So therefore, I want you to go look and see what they gave me. They gave me cosine of theta. Guys, remind me, what is the cosine of theta equal? So, toa. What does cosine equal? Ca, right? What does that equal?
Opposite.
C-A-H. Remember, so toa. So cosine is adjacent over hypotenuse. And why would I do that? Guys, what is the adjacent? The adjacent is 2. And what's the hypotenuse? It's 3. So, what do I do to find the opposite? Pythagorean theorem, right? A squared and you can put 2 there if you want, plus b squared, we don't know, that's the opposite leg, equals c squared, that's 3. Again, 2 squared is 4, so we have 4 plus b squared equals 9, 3 squared. Don't I subtract 4? What's 9 minus 4? So b squared equals 5. What do we do last? We take the square root of 5. Will that reduce? Square root of 5?
You can do, well, I can do it like you did in the last one.
Can you pull a perfect square out of it though?
Yeah.
5? 4 won't go into 5 either.
It's not good, actually.
It has to divide evenly into it. That's why when we go through that whole list, we're looking to see the one that divides evenly. So nothing, 1 would go into it, but it won't help me. So my opposite side is square root of 5. All right, ready to answer the rest of the questions?
Yeah.
All right, I'm gonna erase this one. Let's just answer the questions. Sine. Opposite over hypotenuse, right? Sine. Square root of 5 over hypotenuse 3. Square root of 5 over 3. That was done. So can we do cosecant pretty quick?
Yeah.
Isn't that 3 over square root of 5? Then we're going to rationalize the denominator. So we're left with 3 square root of 5 over 5. Some of you guys will get so comfortable with this, you'll just do that automatically. Yes?
I was just wanted to ask, can you just write it like that? Or?
Absolutely. If you get comfortable with it, absolutely. We already did they told us cosine 2 over 3. So what's secant? 3 over 2. How about tangent? TOA, right? What's that? Opposite
Square root of 5
over
2.
adjacent 2. Square root of 5 over 2. That one's done. Cotangent, flip it. You got 2 over square root of 5. Again, if you're comfortable with it, rationalize it in your head, but the answer is 2 square root of 5 over 5. And that's it. That's all there is to these problems. Okay? So, is everybody good with that one, or do y'all want me to do number 6 as well? Good? Okay, let's go to the last ones then. And here's the deal with these last problems. Because 45, 45, 90, and 30, 60, 90 are special type of right triangles. Are y'all listening to this? No matter what the side lengths are, they will always relate to each other in a specific way. They always follow the same ratios. And here's what those ratios are. For a 45, 45, 90 degree angle triangle, your side lengths that are your legs, they will always be a 1-to-1. So if one side's 7, the other will be 7. If one of them's 19, the other will be 19. They always follow that same rule. And the side opposite the 90 degree angle, your hypotenuse, always then is square root of 2. So if the side length was 5, the hypotenuse is 5 square root of 2. Always. For a 45, 45, 90 degree triangle. For a 30, 60, 90 degree triangle, across from the 30 compared to the hypotenuse is always 1-to-2 ratio. Across from the 30 compared to the across from the 90 is always a 1-to-2. And then across from the 60 is square root of 3. So because of that, this is what happens. Your values for these are always consistent. So for example, sine of 45. Because they always follow these ratios, no matter what your side lengths are, how would I do the sine of 45? Isn't it opposite over hypotenuse? Well, opposite is what? 1. Hypotenuse is what? Square root of 2. Rationalize the denominator. So sine of 45 will always be square root of 2 over 2. Now, look at cosine, guys. Isn't it adjacent over hypotenuse? Well, if I'm going from the adjacent one, isn't the adjacent leg the same as the opposite leg? So So it's still going to be 1 over square root of 2, which rationalizes to what? So sine and cosine of tangent will always be square root of 2 over 2. Okay? And then lastly, tangent, this is easy. It's opposite over adjacent. Isn't that 1 over 1? So the tangent of 45 degrees will always be 1. Now go to your calculator real quick for me. Click mode. Scroll down to where it says radian or degree and make sure degree mode is on. Now go back out to your calculator after you've done that and type in sine of 45. Now click cosine of 45 and tell me what you notice. Exactly the same. Is it 0.7 something? Okay, type this in for me. Square root of 2 over 2 or divided by 2. What do you get? Square root of 2 over 2 is what? Same answer, 0.7 something, right? If you're typing it in dead left to right, you hit the square root of 2 like that, you've got to close that off before you divide by 2. Or it won't work.
Yeah, it was all in the square.
Alright? So that's what was happening to yours. That's why I would rather you use square root of 2 over 2. You don't have to worry about parentheses. So, alright, now, last, type in tangent of 45. Let me prove that it's 1. Is it? Okay. Now, another cool thing, and I'm going to use red to highlight 30 degrees, and I'm going to use blue to highlight 60 degrees, okay? So watch this. Sine of 30. Okay, so we're coming from this angle. Sine is, right? Sine is opposite over hypotenuse, sine. So, okay, get it? Opposite over hypotenuse. So the sine of 30 is always 1/2. Click it in your calculator. Click it. Type it. Sine 30 equals. Now, I want to move now to the 60-degree angle. Look. What is 1 compared to the 60-degree angle? It's the adjacent leg. So cosine of 60 is adjacent leg over hypotenuse. So cosine of 60 is the same as what? Sine of 30. And that is not a coincidence. That's always the case. In a 30, 60, 90-degree triangle, the sine of 30 and the cosine of 60 are the same. Because they're both talking about the same side. For sine, it was the opposite. For cosine, it's the adjacent. So guess what else is the exact same? Cosine of 30 and sine of 60. Same. Look. Let's start with cosine of 30. Cosine of 30 is adjacent over hypotenuse. That's square root of 3 over 2. But guess what the sine of 60 is? The sine of 60 is opposite over hypotenuse. Same fraction. Square root of 3 over 2. So, the sine of 30 and the cosine of 60 are the same. And the cosine of 60 and the sine of 30 are the same. Okay? I think I may have said the same thing both times. But you get what I'm saying? The sine of 30, cosine of 60 have to be the same. Cosine of 30, sine of 60 have to be the same. And then the tangents and cotangents, they're the opposites. Okay? Take the tangent of 30. Let's start with the tangent of 30. Tangent of 30 is opposite. What's the opposite of 30? 1. Over the adjacent, which is square root of 3. Now, again, remember, you have to rationalize that denominator. So when we multiply by square root of 3 over square root of 3, you'll be left with square root of 3 over 3. Can y'all see that? Sorry, it got a little jammed in there. But the tangent of 60, look, right here. Tangent of 60 is opposite square root of 3 over adjacent 1. So square root of 3 over 1. The exact opposite of that last problem. Of course, the square root of 3 over 1 will reduce to what? Square root of 3 over 1 reduces to what? Just square root of 3. You don't have to put the over 1. And that's it. That's all there really is to this. Okay? It's pretty tough. But the point I want to make, the reason I even want us to go through those is because no matter how big my 45, 90 degree triangle is, or no matter how big my 30, 60, 90 degree triangle is, when it comes to sine, cosine, and tangent, for all of those angles, they always follow the same rules. Never an exception. Okay? So, your homework tonight is from this worksheet I'm handing out, numbers 2 through 16 even. 2 through 16 even. That's 8 problems, but they have same kind of problems where you have to do the sine, cosine, tangent of all the different angles. So 8 problems really means a little bit more than 8, but you guys can handle it. Okay? Any questions? I'm going to stop the recording then.